All right, let's get into it. Today, we're basically becoming mathematical detectives. Our mission? To crack the case of polynomial equations and find their real roots. Now, I know that sounds a little intimidating, but think of it less like a dry math problem and more like a mystery we need to solve. And to do that, we're going to build the perfect toolkit. So let's open up the case file. Okay, here it is. This is our case, our central piece of evidence. This equation is the mystery we have to unravel. Our whole job is to figure out what values of x make this statement true. Find the x that marks the spot. In the math world, we call these the roots, but for our purposes today, they're the culprits we're hunting down. So what's the plan? How are we going to crack this thing? Well, our investigation is going to have four main parts. First up, we'll try the most direct approach we have, factoring. If that doesn't work, we'll move on to a more clever tool to create a list of likely suspects. After that, we'll uncover a really cool 2-for-1 clue that deals with a different kind of root. And finally, we'll put it all together into one complete toolkit, so no root can ever hide from us again. All right, tool number one. This is our go-to, our most straightforward method. When it works, it's amazing. It's like getting a full confession right at the start of the investigation. We call it factoring. So what is factoring? It's really just the art of breaking things down. We take a big, complicated polynomial and try to split it into smaller, simpler pieces. For our case, that big, long equation, we could try grouping terms together, looking for something they have in common. If we can successfully break it apart, finding the roots becomes super, super easy. Now here's where things get interesting. As you're factoring, you might find the same clue, the same piece of evidence popping up more than once. You might see the exact same factor, say, twice. And that's not a mistake. That's a really important clue in itself. When that happens, it leads to something we call a multiple root. It just means that a particular solution is so important to the equation that it actually counts more than once. It's a key detail that helps us understand the full picture of what the polynomial is doing. Okay, so factoring is awesome, but, and this is a big but, it doesn't always work. Sometimes the lock just won't pick. So what happens when our equation, like the one we're trying to solve, just refuses to be factored nicely? Well, that's when we have to call in the forensics team. Right. So when factoring doesn't work, we don't just give up and start guessing randomly. No way. We get systematic. We create a definitive lineup of every single possible rational suspect. And to do that, we have an absolutely brilliant tool at our disposal. Let me introduce you to the rational roots theorem. Now, the cool thing about this theorem is that it doesn't just hand you the answer. It does something much smarter. It gives you a complete, and more importantly, finite list of all the possible rational roots. It takes what seems like an infinite number of possibilities and narrows it down to just a handful of suspects to investigate. Let's use it on our case, that 2x cubed minus 5x squared minus 9x plus 18 equals 0 equation. Step 1, we list all the factors of the constant term, which is 18. So that's plus or minus 1, 2, 3, 6, 9, and 18. Step 2, we list the factors of the leading coefficient, which is 2. That's just plus or minus 1 and 2. Now for step 3, we just make fractions by dividing all the factors from step 1 by the factors from step 2. This gives us our final suspect list. Plus or minus 1, 2, 3, 6, 9, 18, and also plus or minus 1 half, 3 halves, and 9 halves. That's it. Our search is now confined to just those numbers. We just have to test them out. But hold on, our investigation isn't quite done. Not all roots are nice, clean numbers or fractions. Sometimes we run into a totally different kind of suspect, the irrational root. And these guys have a very interesting habit. They almost never work alone. Yep, that's right. The numbers we're hunting for aren't always going to be simple. Sometimes they're irrational. Those messy, endless decimals that involve things like square roots. To be a true master detective, we need a tool that can handle them too. And that tool is the irrational root theorem. This is one of my favorite clues in all of math. It's just so elegant. It says that if you find one irrational root, something like 3 plus the square root of 2, then you automatically, without doing any more work, know that its partner, its conjugate, 3 minus the square root of 2, has to be a root 2. They always come in pairs. Seriously, think of it like a buy one, get one free sale. The second you confirm that one of these is a solution, you get its partner for free. It's an incredible shortcut that can literally cut your investigation time in half. So let's just step back for a second and look at the powerful set of tools we've just put together. We're not just staring at a scary, complex problem anymore. We are now fully equipped with a detective's kit ready to solve this thing. So here is your strategy, your game plan, for any case you come across. First, always try to factor. It's the fastest way to get an answer. If you get stuck, pull out the rational root theorem. Create that lineup of suspects and start checking them. And all along the way, keep the irrational root theorem in the back of your mind. If you find one, you've found its partner. Case closed. Factoring, the rational root theorem, and the irrational root theorem. That's the whole shebang. Together, these three tools create a powerhouse system for tracking down every single real root of a polynomial equation. With this kit, you're ready for pretty much any case that comes your way. But did you notice that word I kept emphasizing? Real? If this entire toolkit is designed to find the real roots, it kind of begs a question, doesn't it? What other kinds of roots could possibly be hiding out there, somewhere beyond the real numbers? Well, that's a mystery for another time.